Hello everyone, my name is Ajay. In this video, I am going to talk about a very insightful review article regarding the photocatalytic hydrogen peroxide generation. This review explores how we can shift from conventional method of H2O2 synthesis to light-driven synthesis of hydrogen peroxide. To understand why this shift is so important, let's take a look at the big picture here. The centralized model depends on fossil fuels and expensive catalysts, not to mention the logistics headaches of shipping hazardous chemical around the globe. The review, however, points about the hydrogen peroxide synthesis on the site where you need it, with zero waste. As the article emphasizes, researchers are looking at everything from metal organic frameworks, covalent organic frameworks, to various inorganic photocatalysts and organic polymers. So how does the chemistry actually happen? To really understand this, we need to look at our material through the lens of semiconductor physics. When our photocatalyst is exposed to light irradiation, it absorbs solar energy. If the incoming light energy has enough energy to overcome the material's band gap, it excites the electron. These electrons essentially jump from their resting state valence band to high energy conduction band. This charge separation is the driving force of the whole process. These photo-generated charge I should say, travels on the surface of the catalyst, and they are involved in the two key reactions. One is ORR, which stands for oxygen reduction reaction, and another is WOR, water oxidation reaction, to create H2O2 and keep everything balanced. Well, the goal is to keep these charges separated long enough to do their work before they are simply recombined and waste that energy. Okay, let's talk about more metal organic frameworks. MOFs are huge focus in this review because they are so customizable. However, they often need a little help to be truly efficient. The article highlights 5 ways through which we can boost their performances. So first we can combine them with the co-catalyst like a zinc sulfide. Second, we can use defect engineering, essentially building tiny flaws into material to create more active spores. Third, there is a ligand modification where we can tweak the organic connectors to catch more visible light, basically to enhance the light absorbance spectrum towards the higher wavelength. We can also use two-phase system to improve the reaction environment. And finally, addition of a new metal site within the framework to speed up charge transfer. Each of these strategies is a targeted way to make the framework more harder. Okay, now let's talk about another sophisticated way to enhance activity of the photocatalyst, which is a scheme heterojunction. Think of this term as team up between two different photocatalysts. As you can see in the diagram, it works a bit like a traffic controller. By pairing or combining two materials, we create an internal electric field that pushes the low energy charges out of the way while keeping the high energy electrons and holes separate, and which can later combine with or involved in ORR and WOR reactions. This spatial charge separation is a total game changer for efficiency. Okay, finally, to wrap everything up, what does this review tells us about the future of hydrogen peroxide? The big takeaway is that we now have a roadmap for moving from massive carbon heavy factories toward a cleaner, localized future. But the next real hurdle for the community isn't about the initial performance of the photocatalyst. Actually, it is about the stability. We need these materials to remain active and durable for long-term industrial cycle. At last, I would like to end by thanking my supervisor, Professor Priyanka Verma, and my lab mates, IIT Delhi, for their constant support and funding. If you like to see full data and literature behind these strategies, please scan the QR code here on the screen. Thank you all for your time and attention.